Yes, welcome to you all for the next subsequent presentation. So, in this presentation, I would like to explain you the continuation of the previous problem actually. So, in the last problem, we have seen the force voltage analogy of the given problem. Okay, so this we can see in this lecture. This is lecture number 45, lecture number 45. This is the same problem. Let us consider the same problem which we have considered in our previous presentation. So this is the reference actually. This is the reference basically. We have two blocks. This is M1 and another is M2. Clear? So for this M1, we are applying here f of t, and for this M1 you have the corresponding displacement as x1 here, and for this the corresponding displacement is sorry, x2, and here you have the frictional coefficient as b1, and in between these two you have two common elements. This is we have as k1, and then one frictional coefficient as it is b12. It is given like this in the problem, that's why. And the another end of this block 2 is connected to some reference. Actually here if you see, this difference is given like this here, but it is not connected here. Instead of this we are applying force here on M1. Okay, so M2, it is connected with the K2 spring constant, and then B2 the frictional coefficient B2. Anything is left over? Nothing. So we have covered everything. So this is the given problem which we have seen in our previous presentation. Okay, so in this presentation I would like to explain you about the force current analogy of this force current analogy of the above circuit. So for force current analogy of above diagram, so it is simple as we have seen in our previous presentation, and you can write the differential equations as the same whatever we have in our previous presentation, the same expressions in force current analogy also. Okay, so we can have two differential equations here basically. So solution part I am I am writing here the solution part. You can write the differential equation with respect to M1. Okay, the differential equation, what is the differential equation with respect to M1, block M1. What is the differential equation here? It is M1 into d square x1 by dt square plus it is b1, this particular dx1 by dt, clear, and then next k1 plus it is k1 of x1 minus x2, then b12, it is b12 of d by dt, means for b it comes first derivative x1 minus x2 clear, is equal to your f of t. Call it as equation number 1. Same, whatever the expression we have in previous slide, the same will come here also. This is your first expression. Similarly, what is the second expression with respect to x2 or with respect to m2? The second differential equation. This is the first differential equation with respect to m1, and I will write the differential equation with respect to m2. Clear? With respect to m2, the differential equation with respect to m2. What it comes? How it comes? It is m2 into d square x2 by dt square plus k2 into x2 plus b2 into dx2 by dt. Clear? Then common elements k1 of x2 minus x1 plus b12. Clear? D by dt of x2 minus x1 equal to 0. All this as equation number 2. This is the second differential equation. Remember that sometimes in our competitive examinations like UPSC CES examination, you will have the differential equation part. Basically, they will ask you to, write the differential equations for the given, uh, block diagram. So these are the two expressions basically. Now I can erase this total diagram and I will write these two equations again. Remember that. So in this problem, what we are doing is that we are just trying to draw the electrical equivalent circuit of this given mechanical block diagram, actually mechanical system. So the given system is a mechanical system basically. For this given mechanical, we are trying to draw the equivalent equivalent circuit basically, is it not? So therefore if I draw those two equations again for your quick reference, I will draw those two equations here like this. So it is like this. It is m1 d square x1 by dt square. Again I will write for our okay, and then next is the b1 into dx1 by dt plus k1 into x1 minus x2 plus b12 d by dt of x1 minus x2, clear, is equal to f of t. This is your first differential equation. Not required to give any equation number for this, just I am writing another time. And the second equation is your m2 into d square x2 by dt square, the second differential equation, and then your k2 x2 plus b2 dx2 by dt plus, and then common elements same k1, here it comes x2 minus x1 plus it is b12 d by dt of x2 minus x1 equal to 0, right? These are the two differential equations. Now just remember that in force voltage and force current analogy, in force current analogy, how the mechanical elements converted into equivalent electrical part, basically how these are going to convert the equivalent electrical part actually. So if you see that your m, okay, So starting from F, you can say, you take first element as force because applied element is force here. What are the basic elements? F of t, then M, and then normally B, and then K, and then X. These are what now? What are the elements? These are what basic elements. Your F of t will be converted into I of t basically in force current analogy. So force is converted to your current, M is converted to capacitance C, B is converted to 1 by R, K is converted to 1 by L, X is converted to flux, electric flux, and then X dot nothing but dx by dt. This is equal to further d phi by dt. This is equal to V, voltage. Remember this. Okay, F of t is converted into I of t, current, because it is a force to current analogy. So force will be converted to I of t, and the mechanical portion here, a mechanical element M converted to electrical equivalent, electrical element C. B corresponds to your 1 by R. Obviously it is conductance. K is equal to 1 by L, X equal to phi, X dot is equal to this one. So now what we have to do is that now all these electrical equivalent for the given mechanical, you should substitute all these in these expressions. That's it. So remember that not required to apply any Laplace transformations here. Remember that, because we are not finding out here any transfer function. That is not our objective here. Our objective is to draw the electrical network only for the given block diagram. Therefore, if you write the force current by using force current analogy, by using, you can write by using force current analogy. So as I have explained in the previous presentation, here also it is very simple. Remember that force to current analogy, current is nothing but actually from Ohm's law, V is equal to I into R. And from this force to current, no, force to current, that's why you write the expression from Ohm's law, I is equal to V by R. Means that you must write all these elements in such a way that that should equal into I. What is the I value? Means, okay, I is equal to V by R form. Actually we have to write, okay, I is equal to V by R. That is nothing but actually, so here M means mass element. It is actually M1 is nothing but first mass element. So your M is equivalent to capacitance C, and B is equal to, however, it is R nothing but it is 1 by R. This is equal to K is equal to 1 by L, R nothing but inductance, or similarly this is again resistance. Okay, this is resistance only, B12, and your F of t is equal to I of t. This will be converted as your I of t. And same way here also, wherever M is there, that is capacitance, K 1 by L, B 1 by R, or 1 by R2, whatever it is. Now for this, if you, this is what the capacitive element, nothing but you must write this particular as I is equal to V by R form is nothing but what is the current in capacitance, what is the current in the capacitor element, that you should write actually. What is that basically? If you take the capacitance, C, assume that Vc is the voltage across the capacitor, assume that I is current flowing through this, therefore from here Vc is equal to, what is that, 1 by C integral of I dt. Clear? This implies, so integral of I dt is nothing but, so integral of I into dt is equal to C into Vc. Clear? Cross by taking the cross multiplication. Therefore C will come here. Okay, C into Vc equal to integral of dt. I want current only. So I want I value. So we have integration here. So if I want current value, then you differentiate on both sides. If you differentiate, differentiation integration will be cancelled out. You will have I. Then if you take the differentiation, C is equal to dVc by dt. That is the current actually. This is the current equivalent. This is what the current IC means, current flowing through the capacitor. Means that what? So your expression must be nothing but C1. Wherever C is there, M1 is there, you write C1 into dVC1 by dVC1 by or dV1 you can take V1. Vc nothing but capacitance. Normally V1 you can write in that way. So similarly, take the resistance value. What it will come actually? B1 is the resistance. Okay, voltage. Remember that capacitance into voltage. That is what current. Current I is equal to V by R form. Therefore, obviously, what you will have here? V dx by dt nothing but V1. Clear? So this is what for capacitance basically. If you take the second element B1, it is dx1 by dt. So for dx1 by dt is nothing but what? D phi 1 by dt. No, I already explained here. Why x equal to phi, then dx by dt is equal to d phi by. Further d phi by nothing but your v nothing but v1. Means that dx by dt 1 nothing but v1 actually. Similarly, k1 is equal to what? 1 by L1. I mean k1 is equal to 1 by L. Therefore 1 by L is nothing but what is the current flowing through that in inductor element. So this is inductor, let us say L value, and VL is the voltage across capacitance. Assume that current is flowing through this. Therefore VL is equal to L into di by dt, basically voltage relation. This equal to what I can write? Di by dt is equal to 1 by L into VL. I want I. Then if I want I, then you must integrate on both sides. Then differentiate will be cancelled out. Then 1 by L into VL into dt. So means that this is what current IL is equal to 1 by L into VL in the form actually. Very simple, no? So likewise, this principle if we apply, then definitely your equation becomes very easy. Very, very simple. I think you understood. So by using your force current analogy, then your first equation, this particular first one becomes as C1, then dV1 by dt. Clear? It is B1 is equal to 1 by R1, because B1 take R1, 1 by R1. So it is obviously you will have V1 here, plus K1 is nothing but 1 by L1. Here integral of what is this? I1 minus I2 into dt, plus B12 is nothing but 1 by R12. What is this? What is this? B12. Clear? It is V1 minus V2 is equal to what is that? I of t. That is what? From this equation. This equation will become like this. Similarly, the second equation becomes how? Similarly, this equation becomes C2 into dV2 by dt plus K2. K2 is nothing but 1 by L2. Here X2 nothing but integral of V2 dt. Clear? Plus B2 nothing but 1 by R2. What is dx2? It is V2. Clear? Plus K1 means 1 by L1 equal to integral of this is 1 by L1. It is integral of what is this? V2 minus V1 into dt. Clear? Plus it is 1 by R12 V2 minus V1 equal to 0. This is what. So these are what the finished. Our job is finished. Corresponding mechanical equivalent is given in this. Your M, all is mechanical converted like this. So from these two equations, now you can write that the electrical equivalent circuit. How it look like? It is something like that, no? If you see in force voltage, your RLC parameters are in series, because voltage is equal to I into R, nothing but the voltage. in voltage analogy, I mean force voltage analogy, all those elements will come into series. Whereas in force current, remember that R, L, C comes in parallel to each other. In parallel to each other. That's it. So I think you have understood this, how we converted. Now I will draw the electrical equivalent circuit. What is the electrical equivalent circuit? So consider these two expressions. Consider now, you consider these two expressions now. From these two expressions, now I of t is normally the input current basically. So V1 and V2 are the two nodal voltages. Let us say this is V1 and some V2 will be there, nodal voltage. You can take like that, because with respect to node you can represent all as in parallel combination. C1, so definitely your C1 is there here. Let us see how it look like. R1, this is R1, this one, this is 1 by L1, this is common. Is it what is this? 1 by L1 is nothing but I think it's not I1, it's V1, sorry, it's V1, V1 minus V2, okay, V actually, not I, because current equivalent, no, so your current comes in terms of voltage. Therefore if you see 1 by L1 nothing but your L1, 1 by R2, V1 minus V2, between V1 and V2, V1 minus V2 nothing but this particular L is there in between V1 and V2, means in between these two your L will be there, it should be in between these two. Similarly your R also common. So here, so therefore this means that in between V1 to V2 you can represent L, I mean L1, L1. Similarly R12 you can represent like this. This is your R12 common. So your I of t is something like this here. You can represent your I of t here, say something like this. Okay, and then coming to here, the second equation C2 is there. Therefore, definitely your C2 will be here, and your L2 definitely L2 is there. Clear? And then 1 by R2, definitely you have resistance also like this R2, and these two, however, these are the common elements, there is no equal to 0. That's it, finished your job. This is what the electrical equivalent basically. See how easy it is. This is the corresponding. If you see in this, if you compare these two expressions with this electrical, so here the RLC, RC or RLC will be in parallel combination, and whatever the common elements are there, no, that comes like this in between two voltages. In between two voltages, however, the I of t is the input here. So this is what the electrical equivalent in force current analogy. Force current analogy. Clear? I think you got it. You understood well. I hope that. So with this, I will finish off today's this particular presentation, and with some more examples we will continue in our subsequent presentations. Okay. Thank you one and all.